When you look up at the night sky, you are looking out into the grandest of all stages, the universe. In its simplest definition, the universe is everything. It is all of space, all of time, and everything that exists within them. This includes every star, every planet, every galaxy, and every speck of dust floating in the cosmic void. It also includes you, me, and every living thing that has ever been. The universe is the ultimate container, the sum total of all matter and energy, governed by the fundamental laws of physics that we strive so hard to understand. It is a story that has been unfolding for billions of years, and we are fortunate enough to be living in a time when we can begin to read its pages. Think of space as the three-dimensional arena where everything happens. It has length, width, and height, giving every object a location and a volume. You can move up or down, left or right, forward or backward through space. But space is not the whole story. There is another dimension that we all experience constantly. Time. Time is the relentless forward march from cause to effect, the unceasing flow that separates the past from the future. You cannot have an event without both a place and a moment. The universe, therefore, is not just a vast emptiness dotted with objects. It is a dynamic, evolving entity, where space provides the stage, and time provides the script for the cosmic drama. The scale of the universe is almost beyond human comprehension, a concept that can make you feel both incredibly small and profoundly connected. Our current best estimate for the size of the observable universe, the part we can see from Earth, is a staggering 93 billion light-years in diameter. Within this immense sphere, astronomers believe there could be as many as 2 trillion galaxies. And if each of those galaxies contains, on average, hundreds of billions of stars like our Sun, the total number of stars could reach a septillion, which is a 1 followed by 24 zeros. That's more stars than there are grains of sand on all the beaches of Earth combined. And here is a mind-bending thought. That vast expanse is only the part of the universe we can see. The light from anything beyond that cosmic boundary has not had enough time in the 13.8 billion years since the universe began to reach us. Some physicists, based on calculations and cosmological models, suggest the total universe could be at least 250 times larger than what is observable. If that were true, our entire known cosmos would be just a tiny, insignificant bubble within a much grander, unseen reality. We are like sailors on a small raft in the middle of a boundless ocean, able to see only to our horizon, with no knowledge of what shores might lie beyond. For centuries, we thought of space and time as separate and absolute. Space was the fixed, unchanging backdrop against which events unfolded, and time was a universal clock that ticked at the same rate for everyone, everywhere. It was a simple, intuitive picture of reality. But in the early 20th century, a brilliant mind came along and completely shattered that notion. That mind belonged to Albert Einstein, who showed us that space and time are not independent entities. Instead, they are intricately woven together into a single, four-dimensional continuum. He called this unified fabric space-time, and it fundamentally changed our understanding of the cosmos. Imagine a giant flexible sheet of rubber stretched out taut. This sheet represents space-time. In a universe with no matter or energy, this sheet would be perfectly flat. Now, if you place a bowling ball in the center of the sheet, what happens? It creates a dip, a curvature in the fabric. This is exactly what Einstein proposed in his theory of general relativity. Mass and energy warp the fabric of spacetime. The more massive an object, the deeper the curve it creates. This simple yet profound idea is the very foundation of our modern view of gravity and the universe. It tells us that objects don't move because of a mysterious force pulling on them, but because they are following the curves in spacetime. This linkage of space and time has some truly strange consequences. Einstein's theory of special relativity, which came first, showed that how you experience space and time depends on how you are moving. The faster you travel through space, the slower you travel through time, relative to a stationary observer. This isn't science fiction, it's a measurable reality known as time dilation. Astronauts on the International Space Station, for example, are moving at thousands of miles per hour, so they age ever so slightly slower than we do on Earth. The effect is minuscule for them, but it proves that time is not absolute. It is relative, personal, and inextricably linked to space. So, the universe is not just a collection of objects existing in a static void. It is a dynamic, four-dimensional tapestry where every event has both a spatial coordinate and a temporal one. You are not just at a certain location, you are at that location at a certain time. The Earth is not just orbiting the Sun, it is following a path through the curved space-time created by the Sun's immense mass. Every movement, every interaction, every cosmic event is a journey through this unified fabric. Understanding space-time is the first step toward understanding the fundamental nature of reality and the grand cosmic dance of which we are all a part. Gravity is the great architect of the universe. While there are other fundamental forces, it is gravity that operates on the largest scales, shaping the cosmos and dictating its evolution. As Albert Einstein revealed with his theory of general relativity in 1915, gravity is not a force in the traditional sense, but rather the effect of mass and energy warping the fabric of space-time. Think back to our rubber sheet analogy. A planet, a star, or an entire galaxy is like a heavy object placed on this sheet, creating a depression. Smaller objects, like a marble rolling nearby, will naturally follow the curve and circle the heavier object. This is what we perceive as an orbit. This elegant concept explains why planets orbit stars, and why moons orbit planets. The Earth is not being pulled by an invisible string from the Sun, it is simply following the straightest possible path through the curved spacetime created by the Sun's enormous mass. This curvature dictates the motion of everything in the cosmos. It's what pulled together the primordial gas and dust to form the first stars and galaxies. It's what holds those galaxies together in massive clusters and superclusters, creating a vast cosmic web of matter that stretches across billions of light years. Gravity is the silent, relentless force that built the magnificent structures we see in the universe today. The more mass you concentrate in one place, the more extreme the curvature of spacetime becomes. If you squeeze enough mass into a small enough volume, the curvature can become so intense that nothing, not even light, can escape its grasp. This is the origin of a black hole. A black hole is not a cosmic vacuum cleaner. It is a region where spacetime is so severely warped that all paths lead inward. It represents the ultimate victory of gravity, a point of infinite density, where our current laws of physics break down. Black holes are a dramatic and powerful confirmation of Einstein's theory, showing just how profoundly mass can bend the reality around it. On the grandest of scales, gravity is locked in an epic struggle that will determine the ultimate fate of the universe. For billions of years, gravity has acted as a brake on the expansion of the cosmos, pulling galaxies toward one another and trying to slow the whole system down. It was long thought that gravity would either eventually win, causing the universe to collapse back on itself in a big crunch, or that the expansion would slowly coast to a halt. However, as we have discovered more recently, there is another mysterious player in this cosmic game, a force that is fighting against gravity and accelerating the expansion. The story of the universe is the story of this cosmic tug-of-war. Our universe has a birthday. According to our best scientific model, known as the Lambda CDM model, everything we know began approximately 13.8 billion years ago. This beginning is what we call the Big Bang. Now the name is a bit misleading. It wasn't an explosion in space, like a bomb going off. It was an explosion of space itself. At the very beginning, the entire observable universe, all matter, all energy, all of space-time, was compressed into a point of unimaginable density and temperature, a singularity smaller than an atom. We don't know what, if anything, came before it, but from that singular moment, the universe began to expand and cool, a process that continues to this day. In the very first fractions of a second after the Big Bang, a truly extraordinary event is thought to have occurred: cosmic inflation. In a period shorter than the blink of an eye, the universe underwent a radical and exponential expansion, swelling in volume by a factor of at least 10 to the power of 78. This is like taking an object the size of a single proton and having it grow to the size of a grapefruit almost instantaneously. This incredible burst of expansion smoothed out the universe, explaining why it appears so uniform and flat on large scales today. It was the most dramatic growth spurt in cosmic history, setting the stage for everything that followed. After inflation ended, the universe was still incredibly hot and dense, a seething soup of pure energy. As it continued to expand and cool, this energy began to condense into matter, following Einstein's famous equation, E equals mc squared. a quark-gluon plasma formed which then decayed into the first fundamental particles like protons and neutrons. For about 380,000 years, the universe was an opaque fog, as light particles, photons, were constantly scattered by free-floating electrons, but as the universe cooled further, protons and electrons combined to form the first neutral atoms, primarily hydrogen and helium. This event, known as recombination, made the universe transparent for the first time. The light that was freed during this era of recombination is still traveling across the cosmos today. We detect it as the cosmic microwave background, or CMB, a faint, uniform glow of radiation coming from every direction in the sky. The CMB is the oldest light in the universe, a fossil relic of a time when the cosmos was just a baby. It is a snapshot of the universe at 380,000 years old, and its tiny temperature fluctuations are the seeds from which gravity would later grow the vast cosmic structures, the stars, galaxies, and clusters of galaxies that we see today. The Big Bang Theory, supported by overwhelming evidence like the CMB, is our most successful account of our cosmic origins. For a long time, the prevailing scientific view was that the universe was static and eternal. It was thought to have always existed and would always exist in more or less the same state. This comfortable notion was shattered in the 1920s by the groundbreaking work of astronomer Edwin Hubble. Using the powerful Hooker telescope at Mount Wilson Observatory, Hubble was observing distant galaxies. He discovered that the light coming from these galaxies was shifted toward the red end of the spectrum, a phenomenon known as redshift. This was a revolutionary discovery, as redshift is a clear indicator that an object is moving away from the observer. Hubble's most crucial finding, announced in 1929, was the relationship between a galaxy's distance and its speed. He found that, with the exception of a few nearby galaxies in our local group, all galaxies are moving away from us. More importantly, the farther away a galaxy is, the faster it is receding. This observation, now known as Hubble's law, could only mean one thing. The universe is not static, it is expanding. This was the first observational evidence to support the idea of a Big Bang, a moment in the distant past when everything was much closer together. Hubble had single-handedly redrawn our map of the cosmos. Now, it's important to clarify what this expansion means. The galaxies themselves are not flying through space, like shrapnel from an explosion. Instead, the very fabric of space itself is stretching, and it's stretching everywhere at once. A good way to visualize this is to imagine baking a loaf of raisin bread. As the dough rises, the raisins, which represent galaxies, all move farther apart from one another. A raisin in the center sees all other raisins moving away from it, and raisins farther away move away faster. No matter which raisin you're on, it looks like you're at the center of the expansion. This is why we see all distant galaxies receding from us here in the Milky Way. This continuous creation of new space between galaxies is measured by what we call the Hubble constant. This value tells us the rate at which the universe is expanding. Current estimates place it around 65 to 75 kilometers per second per megaparsec. A megaparsec is a unit of distance equal to about 3.26 million light-years. So what this means is that for every 3.26 million light-years a galaxy is away from us, it appears to be moving away about 70 kilometers per second faster. This constant stretching of space is the fundamental dynamic of our universe, a process that began with the Big Bang and has shaped the cosmic landscape for 13.8 billion years. For decades after Hubble's discovery, cosmologists debated the future of the universe's expansion. The force of gravity, pulling on all the matter in the cosmos, should act as a brake, slowing the expansion down over time. The big question was whether there was enough matter, and therefore, enough gravity, to eventually halt the expansion and cause the universe to recollapse, or if it would just expand forever at a decreasing rate. For most of the 20th century, scientists worked to measure this deceleration, expecting to find that the expansion was indeed slowing down. What they found instead was one of the most shocking discoveries in the history of science. In the late 1990s, two independent teams of astronomers, the High-Z Supernova Search Team and the Supernova Cosmology Project, were using a special type of stellar explosion called a Type Ia supernova to measure cosmic distances. These supernovae are incredibly useful because they all explode with nearly the same intrinsic brightness, making them excellent standard candles. By comparing how bright they appear to us with how bright we know they should be, we can calculate their distance with great precision. The teams were looking at very distant supernovae to measure the expansion rate of the universe billions of years ago. They expected to see that the expansion was faster in the past. To their astonishment, both teams found the exact opposite. The distant supernovae were much dimmer, and therefore much farther away than they should have been in a universe that was slowing down. The only way to explain this observation was if the expansion of the universe was not slowing down at all. In fact, it was speeding up. This acceleration appears to have started around 4 to 5 billion years ago. After billions of years of being slowed by gravity, some mysterious influence began to take over, pushing space apart at an ever-increasing rate. This discovery was so profound that it earned the leaders of the two teams the Nobel Prize in Physics in 2011. This mysterious force causing the acceleration has been given a name: dark energy. We call it dark because we cannot see it or detect it directly. We only infer its existence from its effect on the expansion of the universe. Dark energy appears to be a property of space itself, a kind of anti-gravity that exerts a negative, repulsive pressure. Unlike matter, whose density decreases as the universe expands, the density of dark energy is believed to remain constant. As the universe grew, matter spread out, and its gravitational pull weakened while the repulsive push of dark energy stayed strong. About 5 billion years ago, dark energy became the dominant force in the cosmos, and the era of acceleration began. Because the universe has a finite age, 13.8 billion years, there is a fundamental limit to how far we can see. Light, the fastest thing in the universe, travels at a constant speed. This means that light from very distant objects has been traveling for a very long time to reach our telescopes. The farthest we can possibly see is the distance from which light has had just enough time to reach us since the Big Bang. This boundary defines our observable universe, a spherical region of space, with Earth at its center. It is not a physical wall or barrier, but simply the limit of our vision, dictated by the speed of light and the age of the cosmos. This boundary is often called the cosmic horizon, or, more formally, the particle horizon. It's kind of analogous to the horizon you see at sea. You know the ocean continues beyond what you can see, but your view is limited by the curvature of the Earth. Similarly, the cosmic horizon marks the edge of the part of the universe we can currently interact with or receive information from. Anything beyond that horizon is, for now, invisible to us. The light from galaxies beyond the cosmic horizon has not yet had the 13.8 billion years needed to complete its journey to our planet. Now, you might think the radius of the observable universe should be 13.8 billion light-years, since that's how long light has been traveling, but you have to remember that while the light was traveling, the space it was traveling through was also expanding. The object that emitted the light we are seeing today from the edge of the observable universe was much closer when the light began its journey. Over billions of years, space has stretched, carrying that object much farther away. When we account for this expansion, the current estimated distance to the edge of our observable universe is about 46.5 billion light-years, making its total diameter about 93 billion light-years. The accelerating expansion of the universe adds another fascinating twist to the story. Because space is stretching faster and faster due to dark energy, there are galaxies beyond the cosmic horizon that are receding from us faster than the speed of light. This doesn't violate Einstein's theory, because it's not the galaxies moving through space that fast, but space itself expanding between us and them. The consequence is that the light from these galaxies will never reach us. They are forever beyond our grasp. As acceleration continues, galaxies that are currently visible near our horizon will eventually be pushed beyond it, their light redshifted into oblivion, and they will disappear from our view forever. For most of human history, our view of the heavens was blurred by the very thing that keeps us alive. Earth's atmosphere, the shimmering turbulent air distorts starlight, limiting the clarity and depth of our cosmic vision. That all changed on April 24, 1990, when the Space Shuttle Discovery deployed the Hubble Space Telescope into orbit 340 miles above the planet. By placing a telescope above the atmosphere, astronomers gained a crystal-clear, unwavering view of the universe for the first time. Hubble became humanity's eye in the sky, revolutionizing nearly every field of astronomy and providing us with images of cosmic beauty and scientific importance that have captured the world's imagination. One of Hubble's most iconic and profound contributions came in 1995. Astronomers decided to take a huge gamble. They pointed the telescope at a tiny, seemingly empty patch of sky in the constellation Ursa Major, a spot no bigger than a grain of sand held at arm's length. For 10 consecutive days, Hubble stared at this dark sliver of the heavens, collecting every faint photon of light it could. The result was a breathtaking image known as the Hubble Deep Field. The once empty patch of sky was revealed to be teeming with life, not biological life, but galactic life. The image contained over 3,000 galaxies, some of them so distant their light had been traveling for over 12 billion years. The Hubble Deep Field was like drilling a core sample through the history of the universe. Because light takes time to travel, looking at distant galaxies is like looking back in time. The image showed a cosmic zoo of galaxies at different stages of their evolution, mature spiral galaxies like our own, chaotic misshapen galaxies in the process of merging, and small, blue primordial galaxy fragments from the universe's youth. Later, after a servicing mission in 2009 upgraded its instruments, Hubble stared even deeper, creating the ultra-deep field and extreme deep field images, revealing thousands more galaxies, and pushing our view back to just a few 100 million years after the Big Bang. The discoveries made possible by the Hubble Space Telescope are immense. It helped us pin down the age of the universe with greater accuracy. It provided crucial evidence for the existence of supermassive black holes at the centers of galaxies. Its observations of distant supernovae were key to the discovery of dark energy and the accelerating expansion of the cosmos. And perhaps most importantly, it transformed our perspective. By showing us a universe filled with hundreds of billions, if not trillions of other galaxies, Hubble has viscerally demonstrated the true scale of the cosmos and our place within it, inspiring a new generation to look up and wonder. With the discovery of dark energy and the accelerating expansion of the universe, our picture of the distant future has become both clearer and more desolate. As space continues to stretch at an ever-increasing rate, galaxies that are not gravitationally bound to us will be carried away faster and faster. Over the next 100 billion years, every galaxy beyond our own local group, the small cluster containing the Milky Way and Andromeda, will be pushed beyond our cosmic horizon. Their light will be stretched to infinite wavelengths, and they will vanish from our sky, one by one. The vibrant galaxy-filled cosmos we see today will become an empty, lonely void. The future of our local cosmic neighborhood will be one of consolidation. The Andromeda Galaxy, our largest neighbor, is currently on a collision course with the Milky Way. In about 4 to 5 billion years, the two giant spiral galaxies will begin a gravitational dance, eventually merging to form a single massive elliptical galaxy, which some have nicknamed Milkomeda. For a time, this new galaxy will shine brightly as the merger triggers a burst of new star formation, but this will be a final, fleeting blaze of glory. The gas and dust needed to form new stars is a finite resource, and eventually, it will all be used up. As trillions of years pass, the era of stars will come to an end. The last, long-lived red dwarf stars will finally exhaust their fuel and flicker out, plunging the universe into a second dark age. The cosmos will become a graveyard of stellar remnants, cold white dwarfs, inert neutron stars, and silent black holes. These objects will drift through the expanding darkness, occasionally colliding but mostly existing in profound isolation. Even these remnants will not last forever. Over unimaginable timescales, protons themselves may decay, and black holes will slowly evaporate through a process known as Hawking radiation, until nothing but a diffuse sea of elementary particles remains. The ultimate end state of our universe, according to this scenario, is known as heat death. It is a state of maximum entropy, where all energy has been evenly distributed throughout the cosmos. There will be no temperature differences, no flow of energy, and therefore no possibility for work, computation, or life as we know it. The universe will become a featureless, homogeneous, and eternally expanding void, a cold, dark and silent expanse dominated by the unceasing push of dark energy. It's a somber end to a magnificent story, a final testament to the relentless march of time and the unyielding laws of physics that have governed the cosmos since its fiery birth.